which I am going to present is Pix2Vox 2 or 3. Okay, so like with the what actually it is and how what it is defining. So like the paper is written over 3D object reconstruction. So like what actually the 3D object reconstruction means, like this is a duster. So I just capture a photo from this duster. Okay, so what happens that like photo will only going to capture this part, but when I feed it to my neural network, so my neural network and all of my algorithms, like it will going to give me a 3D of this object. And by the means of 3D, it's like it's not a front view or the back view, it's the whole 3D. Whole 3D means like the 3D model, so you can rotate it. Even you can use the 3D printer to get a print of that 3D object, so it's like an actual 3D model. So like with the 3D model, like what are the problems that are coming, or what are the previous works that like I'm going to explain a little bit. So the different cases that comes like with the in the research field of 3D reconstruction is like what they used to do is to use an encoder decoder architecture. So what the encode in the encoder decoder architecture, what actually happens that encoder is like encoder, there is a 2D encoder and there is a like 3D decoder. So encoder will going to encode all the information from the image, and 3D and the 3D decoder will going to generate a 3D object. So there are two ways of doing this. Either you can use the multi-view or either you can use the single view. So what the multi-view basically means that you have the object, and for that object you have different images from different pose. For an example, like this is the duster, so you just capture some images from this way, some images from this, and some images from this. So what happens that each of those different pose, basically it is known as pose, will going to have some information regarding that 3D. So the research are like some use multi view and some use single view. So like that you have also maybe heard about, like there are also, without the deep learning, this works also happen like for the construction from the images from the multi view. So what they used to do, they used to like mount a camera, like put this into some kind of good conditions, like the lightning conditions and all that, and they used to mount a camera which just takes some images of some particular pose. Okay, from different particular pose, like capture from this angle, capture from this way, and then they used to fuse. There are different algorithms like visual algorithms, mesh algorithms to construct the 3D. But with the deep learning, like deep learning made it feasible for everyone. Like you do not need to capture the images from certain pose. Like you are not constrained to capture the images from certain pose. You can like capture from different pose and give to your neural network. So this is not in multi-view. Basically, it means that you have images from different views. And with the single view, what it basically means that you just capture the image from only single view, and then you feed it to your neural network. Basically means that your neural network has to come, your algorithm or your model machine has to make the 3D only by a single image. So like in the, like coming back to this paper, so the previous works are like something that they use multi-view. So in the case of multi-view, what they use is there is a paper known as 3D R2R2. So in that they use LSTMs, and in the LSTM what they do, they just fuse the different images from taken from different pose or the camera angles, and then the LSTM tries to remember the information. But what happens that LSTM are not that much of capable to store a long-term memory information. Okay, and with the single view is like that the single view is not capable of constructing such a 3D, because with the, you can also see like with the single view can't able to get that much of information. So in this paper, what they have done, over a brief, they have like what are their basic ideas. They are like that you have different images from taken from different camera angles, and you know that that like with the duster, you just capture an image from here. So this part captures very like this part is more informative other than this part or this part, and then you capture from this part. So this part is more like get into the image, and then this part and this part. So what happens that so it means that some like with the different angles, the different part of that object will going to have more information in that image. Like from one image you're going to have some information, which are like which may be not present in the second image, which may be not present in the third image. So this thing is clear. Yeah. So their idea is basically like you just fuse different images parallelly, taken from different and your model will going to, there is a like something context aware fusion module in this, which will going to get the information, get the most I can say like most aware information, like the in one image, like let's say it has captured some part, okay, which are like this part is captured very good, okay, so it will going to extract the information from this part, and from this part it will going to, taken from this, so this part will going to have this part of information, so it will going to so what happens that they use different networks like parallelly, and they construct a 3D. Okay, let's for an example, you have given the image of this chair from different angles, and they constructed a 3D, so it may be possible that in one in one image, making a 3D of one image will going to capture more information, like it will be going to give a 3D which have more good legs of the chair, and in some part, let's say this part is more clearly constructed, so they just fuse them all together, and finally they get a good 3D of that model. So this part is clear to you.
So is this multi-view?
Yeah, this is actually a multi-view. You can also use it as a single view. So like it's all depends on yours, both multi and single view.
So you pass one view, you get a 3D coordinate for that view.
Yeah.
Multiple views you fuse using some rules.
Yeah, I'll maybe explain that and what is actually happening. So like yeah, so given in the neural network architecture. So now firstly what they have used a 2D encoder to 3D decoder model.
Can you use a red marker?
Yeah. Yeah, so like there are like 2D encoder to 2D and 2D to 3D encoder decoder architecture, and like I have used like this is the image one, like taken from a certain angle, and I have just gotten 3D, okay, of some size, like my, and they have taken I guess 224 into 224 into 3 and RGB or image of 224 square dimension, and they have gotten 3D, let's say I don't know, like the exact shape like the 32 into 32 into 22, okay, so they have gotten 3D, and then they use some then they use the same network and given the different view image, and then they have constructed a 3D also, okay, so like let's say we have an n number of images, so with that so like image and then like this architecture, and then they have got some 3D architectures. Now it's time to like you have got the 3D, and let's say this 3D contains some more good results in the chair part, and this contains some more good in the hands part. So then they fuse it, like, and how they fuse it. So this is like the context fusion model. And before that, like they have trained each of the networks separately. Like this 2D and 3D and encoder decoder architecture is trained separately, and they have like given the, and for the laws they have used the binary cross entropy laws, and yeah, so they have given the, if you see that figure 3, so they have used that ED laws for that. So now the about the context aware fusion module. So like it's quite simple. So like this 3D decoder is having like in the, they have picked the last two layers of the 3D decoder output. So these are like the last two layers of the 3D decoder, and they just concatenate both of them. So let's say it is having some shape of 32 into 32 into 2 square, and 32 into 2 square, and this one is having this is the last layer, so this is having 32 into 32 into 32. So they have just concatenate the last two layers of the output, and then they, and like you have just taken this and taken this and concatenate each of the last two layers output, and then fuse it to like the context scoring network. So it is a network which is like which is having which is like having 3D convolutional neural networks, and in the 3D convolutional neural network, so it's like quite simple. So each of the like this is like the 5 3D convolutional neural network, and it's of size 3 cube. Yeah, 3 cube into yeah, 3 cube kernels are there, and then the best normalization and the value. Like I said, so let's give him a name of PL1, PL2, PL3, PL4, and PL5, and then they like the concatenated and netted output is fused to this context scoring map, and then they got some output. And after getting those output, what they have done, they have passed it to score normalization, and the score normalization is basically simple. Like they have used a formula that calculate the exponential for like the yeah MR, and the output of this is MR basically. So MR, and let's say MR1, MR2, MR, so this is MR1, MR2, MR3, and etc. Okay. So like this is exponential, and this is MR, and like yeah. So IJK are like nothing but the coordinates, like the coordinates of 3D 1, 1, 1, 1, 1, 2, and then they like summation of P is equals to 1 to N. Okay. So MRP, and this is IJK. So what they have done, they have just normalizes each of the coordinates with all of this, and then what they have done, they have just then they have like yeah. Yeah, so what they have done in the last thing, they have taken a weighted, like this will going to give you, and for each of the model output, basically for each of the image you got in 3D, and and you have just find an MR for each of the 3D, and what you can do, like you can use, this will be like the scoring map, and you can use this scoring multiplied by with with your object, and you can like multiply them and sum all of them. So you got like what they are doing, or should I explain in brief? Yeah.
Multiply with the object.
Like no, yeah, with the object. So you have, for each of the object, you have found a score. Okay. So you, what you can do, you can like multiply SR and then the object, corresponding object, that is MR, and for like this you can be like one, for one image you have this, for second image you have this, and for third image you have this. Okay, so you just sum them all together. So what happens then, this will going to come like all together. So all the objects, just you just taken weighted sum of all the objects basically. Okay, now what happens that then what you have done, like you have got your 3D of some shape like this, and finally what happens that most of the papers in the 3D reconstruction, you will see that they just use some algorithms and get in 3D, and then they use a refiner. Refiner basically means the 3D encoder decoder architecture. 3D encoder and 3D decoder. Basically, why they use refiner is that what happens that, like let's say our algorithm, that our model is also not that perfect to construct an actual 3D. So then they use some refiner. It's like in teacher and teacher and student, like a student do something and teacher then corrected it, like the student just made some model and the teacher just used his experience to make it more refined. So then the 3D encoder decoder architecture to make it more refined. Yeah. So like so yeah, so for the encoder in this 2D encoder to 3D decoder, so in the 2D encoder part, what they have done, they have used the pre-trained VGG16 architecture with some layers, and in the 3D they have used the 3D and 3D decoder, basically the 3D convolutional neural network to construct a to get a 3D. Yeah, so like what happens that, like the problem that can occur with the 3D reconstruction is that it actually requires a lot of training, and for that, like currently right now we can't able to we are not having, like in the research field, we are not having that good neural networks that we can use it for any object. So what they have done, they have like taken only one object, that is chair, and then they have used the ShapeNet architecture, to not the ShapeNet architecture, basically the ShapeNet, yeah, ShapeNet 3D plus yeah. So actually ShapeNet 3D is like having models, and you just render them to capture take the different images, and they have used the ShapeNet basically to for the data set, and they have also tried like a different test on the different like Pascal walk and different data sets to test their accuracy. So it shows a very good results in the case of 3D reconstruction. Any doubts?
What do you calculate ground truth for 3D?
Yeah, so let's start with the ground truth. What is ground truth? Is actually a 3D model. So let's say you have a ground truth of this 32 into 32 into 32. Okay, so like actually what is a ground truth? Like let's say there are three types of representation. Actually, I forget this. So first is octaves. Second, like in the three ways you can visualize a 3D. First is the octave, second is the voxel, and third is the point cloud. So I guess they have taken the voxel. Voxel basically means that this is your this. Let's say this is a cube, this room, and you have just divided this room into like four parts. Like you have just cut down this room into small cubes. So what you can do, like you can say that you can say that this cube is, if this cube is filled, that your objects lies here, and if this cube is not filled, that means that your that this is a free space. So for the ground truth, what they have done, like 32 bit, you have a 3D, and then and your network output is also like 32 to 32 to 32 to 2. So what this basically 2 means that either it is occupied, either it is not occupied. And here what is 32 to 32, that this is a cube, and let's say this is the object that is present. So you might found like you also convert that to 32 to 32 to 32 to 2. That means that the locations, that some of the locations are either empty and some of them are either filled.
My question was, how do you get that 32 first? 32? Like, how do
Yeah,
you generate
this one, sir. Yes, sir. We have our 3D model in our data set. Those are actually rendered by using CAD, like computer-aided design softwares. Yeah, so you can like use the softmax and using the binary cross entropy to get your loss, and this is how it works. Anything else?
this fusion model is what we were explaining then.
Yeah, so like this.
That is the loss for this fusion model.
What?
That one.
This one. This is.
That one.
Yeah, this one. So like this is what like no sir, this is not the loss, but this is if you see that context aware fusion model, like how they have take the different parts which are constructed very good and fuse them together. So in that what they have done, they have like they have used this output, the 3D decoder output, and take the last two layers of the 3D decoder output and concatenate them together. And what then they have done, they just pass it to a model which is having five 3D convolutional networks, and they have passed the output of that to SR to normalize it basically over all the generated models. Okay, and then they pass that SR to and then they pass it. Yeah. So then they pass this SR. This SR is basically a weight. Okay. Then they multiply this weight with the corresponding model, and then they sum all of the models together like a weighted sum. So this is how it.
Why do we need two channels in the ground truth if the question is whether it's present or not present? So it would be just 1 or 0.
Yeah. So like let's say like if I just build a 3D. So like, yeah. So what happens that like let's say I have an object that is present over here. So at all these locations where object is not present, that basically means that that it's having the value as a 0. Like so I divide this like into this small voxels. So you can see like this location, this location is having its value as 1, and all these locations having the value 0. So what this basically, why we need two channels is that what it shows, that at this location it shows the probability basically, that either that the in this 2 this having like 0 and in the 2 we are having 1 and 2. Okay, like the 32 to 32 to 32, and then the two things. So one shows the probability of the voxel, either it is like the filled or not filled. So this tells about not filled, and this tells about the filled.
No, I think she's asking, like, it can be done with the sigmoid also, no?
One minus something is not.
1 minus something.
Like it's probability.
Yeah.
It's there means 1 minus something is
Yeah.
not there.
Yeah,
Why do you need 2? It's why you need 2 then.
Yeah, 2. You need 2. Then that means like this shows like if you check this thing, I guess sigmoid. So this shows that this shows about the non-filled part and this shows about the filled part. So when you get your output, so if this 1 is maximum, it comes the maximum. So you can like this one channel is like having some value of 0.799 and this is having the remaining value. So you can say that this is the part that is filled. So you just extract the one part. Getting what I'm saying? If you like, if what is saying like, if we got a probability, so how could we say that what this probability means? It is telling about the filled part or the unfilled part. So you get the probability for both the filled part and the unfilled part. So if the probability is more in the piece of filled part, so you just assign that this part is filled, so you assign that one.
In the sigma,
like basically, yeah.
in the sigma example, you can consider anything less than 0.
Sigma, like it's the softmax actually. It's the softmax.
No.
Softmax also.
For an example, like you're going to get understand like.
So the sum of probabilities we want.
Yeah, the sum of both the probabilities.
Then why can't you just do 1 minus?
Yeah, I can do the 1 minus sum, but what this 1 minus sum is going to tell me?
If that is 0.79, 1 minus something is, if it's like 0.3 means, 0.3 is the probability of not having curve.
But I can, but I can't like, but I can't say like if you just have work on that thing, mask images.
Hey, that's like sigmoid. It's like segmentation wise.
Segmentation, yeah.
Rather than sigmoid. Sigmoid tends to like skew it like so it's 0 or 1.
No, but
tends
they're competing against masks. No, here it's only whether
the same problem. No? It's like how the losses are defined. In sigmoid, you have a clean slope, but
this is
soft
not
max,
loss, right? This is ground truth.
yeah. First listen. It's like a slope, right? Sigmoid, but whereas softmax tends to push you to the edges. So that is more easier to learn for a binary than using a sigmoid. Thank you.
Yeah, same in the like with the mask images, should not like with the mask when we make.
You don't need a beautiful distribution between 0 and 1.
then why don't they use for binary? Why don't they use softmax or
Yeah, actually, I was wrong. They have used the softmax, not the sigmoid one. They have used the softmax. Yeah, I have like misspelled it. Any other doubt? Even like one of the research, if I were to tell it's about the 3D GAN that I was like reading in the December month. So it was like that using the GANs, you just constructed a 3D and then you use that latent vector of it and you just use some that prior information and you just construct, like I just got a 3D of this chair and I used up some more information to construct a beautiful new chair of that. So you have only one image and you construct like the 7 to 8 images, different kind of 3D out of them. So it's like one of the, but the only drawbacks is that you can't construct like in my that I have done. It wasn't like this. I have done something else. So I was restricted to only use the 4 objects: chair, couch, and just like the airplane and one more like the table. Yeah. So this is the drawback of 3D reconstruction right now, which the researchers are facing. Yeah, so